What has a 1 in 10 quadrillion profile and just turned blue near the sun? 3I Atlas, multiple coronagraphs, stereo A, Soho Lasco, goes 19, logged blue-dominated emissions where classic dust scattering says it should go red. We'll walk the rule of 3, either unknown natural physics, an extreme edge case, or technology. Then we connect the prior anomalies, ecliptic alignment within 5 degrees, elevated nickel versus iron, solar center ejection, only 4% water, to show why this isn't a single weird data point. By the end, you'll know exactly what December's Webb-Hubble spectroscopy must confirm or falsify. Why would anything diving toward the sun look bluer when the physics of dust near intense heat says it should trend red? That is the crux of the 10th anomaly. During perihelion, coronagraph data streams show 3I Atlas skewing toward blue-dominated emission right when you'd expect warming dust to deepen the red continuum. If you've watched comets brighten before, you know reddening near the sun is the rule, not the exception. So a blue surge is not a cosmetic change, it's a sign that the engine under the hood might not be the one we think it is. Here's the event as claimed. As Atlas crossed perihelion, independent coronagraphs reported a measurable tilt of the visible output toward shorter wavelengths. The effect shows up in multiple instruments that use different optics and filters, yet the trend points the same way. The blue channel strengthens relative to red during the closest solar pass. The timing matters. The color balance shifts during the period of maximum solar irradiance, not hours or days later when dust usually dominates the view. That locks the anomaly to the heat peak, which tightens the physical options. Now for the tension. Standard dust scattering models near the sun favor a reddened continuum because larger grains and thermally processed particles scatter longer wavelengths more efficiently in integrated light. Even gas-rich comets don't usually flip the entire output to blue. You get a baseline reflectance that slopes gently upward into red, plus familiar emission features riding on top. A broadband blue rise runs against that grain. To make blue dominate, you either push the effective temperature into a regime that glows at shorter wavelengths, or you light up specific emission lines so strongly that they overwhelm the underlying red continuum. That's where Wien's law enters. The peak of a thermal spectrum shifts to shorter wavelengths as temperature climbs. If the blue swing reflects a true thermal peak, you need temperatures far beyond what sunlit dust achieves at perihelion. Passive grains at a few hundred to a couple thousand Kelvin do not peak in the blue. So a thermal interpretation implies either intense internal heating or a concentrated energy source that doesn't look passive. The other option is non-thermal emission, narrow bands or blended features that fill the blue channels without requiring blackbody temperatures at all. Watch the timeline. Pre-perihelion, Atlas glows with a green cast typical of comets with strong bands from radicals like C2. That green bias has been seen time and again in active comets as sunlight pumps molecular transitions. Near perihelion, that signature reportedly yields to a blue tilt that holds across instruments. The change tracks the closest approach to the sun, then relaxes as the geometry and activity change. The sequence suggests a physical switch rather than a calibration quirk that would hit all bands at once. Comet spectra usually mix dust continuum with gas emission. Common contributors include CN in the violet, and bands from C2 and C3 that cluster in the green. Those lines can color the coma, but they don't typically produce a broad blue dominance across wide filters. You still expect the red-sloped dust continuum to anchor the shape, even if gas adds local bumps. Overpowering that continuum demands an unusual surge of blue-weighted emission, or a suppression of dust scattering that is tough to square with perihelion activity. Instrument artifacts always deserve scrutiny. Filter leaks, vignetting, flat field errors, or color matrix coefficients can skew apparent hues. But when separate platforms with different detectors and calibration pipelines report the same directional shift at the same orbital phase, the odds of a shared artifact drop. Cross-instrument consistency acts like a built-in control. You can fake a hue in one setup. You rarely reproduce it across multiple unless the sky itself changed. If this blue dominance holds up under deeper analysis, it slices straight across the standard thermal and dust scattering picture. Passive models expect redder light from heated dust and a balanced blend of gas features, not a wholesale shove into shorter wavelengths at the heat peak. That forces you to account for energy input or emission pathways that don't ride on quiet sunlight alone. So the 10th anomaly isn't about aesthetics. It points to an energy budget that strains a passive body, either hidden heat that pushes emission into the blue or non-thermal processes turned up to levels we don't normally see in solar grazing visitors. And if a single pass can flip the spectral balance that hard, then the earlier oddities start to matter more than curiosity notes. What exactly were those first 9 that primed the odds at 1 in 10 quadrillion? How do 9 independent oddities add up to a profile that almost never happens by chance? You don't wave them away, you stack them. Treat each as an event with its own small probability. If they don't rely on the same cause, you multiply. That's the framework. It's the difference between weird things happen and 10 weird things landed on the same object at once. The product shrinks fast, and before you reach double digits, the odds look less like noise and more like a signal that demands an explanation. Start with the flight path. 3i Atlas cruises within about 5 degrees of the ecliptic, the sun's planetary highway. Interstellar entries should arrive from random inclinations because the galaxy doesn't care about our plane. Hitting our thin disk by chance is possible, but hugging it closely narrows the cone a lot. That kind of alignment can look like intent because coplanar lanes are efficient for rendezvous and transfers. If it's coincidence, it sits in the tail of the distribution, not the center. Now the ejection geometry. Reported material shedding favored a vector aimed toward the solar center. That flips the usual script. Outgassing vents typically throw momentum away from the sun, and radiation pressure accentuates that push. A thrust toward the star runs counter to the standard model. You need non-radial jets aligned just so, or an active process that controls the exhaust. Either way, it's not the default behavior of a sun-warmed porous nucleus. Composition adds a third strike. Elevated nickel relative to iron doesn't match the common cosmic blend found in primitive bodies. Nickel-enriched ratios show up in metallurgy where specific mechanical or thermal properties matter. If that signature is robust, it nudges the discussion from odd rock toward selected material, which carries different implications for how the object formed or was assembled. Then hydration. Only about 4% water is far off what you'd expect from a volatile-driven traveler. Fresh visitors usually carry abundant ices that sublimate and drive activity. Extreme dehydration suggests heavy processing or loss, either by prolonged heating, repeated perihelia, or deliberate removal. With so little water, you need another driver for the coma and tail, or you accept that the body's chemistry departs from garden-variety comet mixes. The sky path stacks with a cultural outlier. The approach vector echoes the coordinates associated with the WOW signal. That alignment is astronomically suggestive because it links 2 unrelated datasets, a one-time narrowband radio hit and an interstellar visitor. No mechanism connects them in this framework, but the overlay is statistically uncomfortable. On its own, it's a curiosity. Multiplied into the set, it moves the needle. Before the blue turn, Atlas had already shown unusual chromatic behavior. Observers noted color ratios that drifted in a way not well captured by typical dust plus gas templates, hinting at time-variable emission features dominating the continuum at phases when dust should settle in. That's not a repeat of the perihelion blue claim, it's a prior record of color instability that erodes the idea of a simple, steady coma. Dynamics add another layer. The non-gravitational accelerations inferred from astrometry didn't follow the standard correlations with brightness and heliocentric distance used for comet outgassing models. The vector and magnitude looked off-pattern, as if the thrust source wasn't tied cleanly to solar heating. That mismatch matters because it speaks to force application, not just how bright the coma looks. Brightness evolution compounded the puzzle. The amplification rates beat what Oort cloud comets typically show under similar insolation. Teams noted the lack of a settled mechanism. If brightness rises faster than conventional sublimation and dust release can support, you either suppress dust while boosting gas in a fine-tuned way, or you invoke an energy input that isn't covered by the usual playbook. Finally, there's a morphological quirk. The coma and tail structure displayed asymmetries that persisted across rotation, implying a stable, preferential geometry rather than random jetting. Long-lived anisotropy suggests controlled vents or structured surfaces that don't smear out with spin, which again resists the default image of a tumbling, eroding snowball. Multiply, don't dismiss. Each of these is low probability under standard models. Together, the product sinks to the 1 in 10 quadrillion territory cited by the statistical framework. Atlas looked extraordinary before the perihelion color flip arrived. With 9 anomalies on the board, the 10th doesn't stand alone. It forces a choice among 3 explanations that pay very different costs in assumptions. Given 10 anomalies, which explanation pays the smallest cost in assumptions? You've got 3 lanes. Either our natural models are missing key physics, we're staring at an extreme stack of coincidences, or we're looking at technology. Each lane has to cover the same payload: a blue-dominated perihelion spectrum, a nickel-to-iron ratio that leans high, a path that hugs the ecliptic, deep dehydration, and reports of ejection vectors favoring the sun. The winner isn't the one that sounds exciting, it's the one that tallies these specifics with the fewest contortions. Start with unknown natural physics. This path says our playbook for Comet and near-sun behavior isn't complete. Exotic outgassing chemistry could push strong emissions into the blue and violet, especially if molecules get pumped in non-LTE conditions, where populations don't follow a simple temperature. You could also tweak the grain story. If the coma hosts an unusual distribution of submicron particles that scatter short wavelengths with high efficiency, the integrated light might skew blue even while larger grains redden. Add solar-wind coupling and plasma interactions near perihelion, charge exchange, electron impact excitation, shock-compressed fields, and you open channels for bright, narrow emissions to outshine a red-sloped dust continuum. For the nickel signal, you'd appeal to fractionation during formation or selective release of metal-bearing grains. Dehydration would point to thermal processing or prior passages that baked volatiles away. This framework pays the cost of revising how comets behave under extreme irradiation and plasma regimes, but it keeps the object natural. The edge case lane takes a different bet. It says every oddity can occur by chance, and Atlas happens to carry many of them at once. The math multiplies: low probability ecliptic alignment, unusual ejection geometry, rare composition, sparse water, and a perihelion color swing. In a Bayesian sense, you attach penalties for stacking coincidences without a shared cause. You can argue selection effects and observational bias. Things that look weird get reported more, but the product still collapses fast. In this framework, you don't change physics. You accept that the tail of the distribution produced a specimen that looks coherent only because we're storytelling on top of independent flukes. Technology asks for the fewest leaps if, and only if, the signals match engineered expectations. An elevated nickel fraction resembles alloys chosen for high temperature resilience. Active thermal management, radiators, or controlled emission systems could create a blue-weighted output at perihelion, where waste heat or power generation spikes under intense insolation. Navigation along the ecliptic fits efficient transfer strategies in our system. Ejecta aimed toward the sun could be thrust vectoring or momentum management rather than outgassing chaos. Dehydration would follow from design choices that avoid volatile loss. This lane pays the cost of introducing a manufactured origin, but it ties the anomalies to functions, materials, heat handling, guidance, without reworking physics. How do we tell them apart? Spectroscopy carries the keys. If the blue dominance is a smooth continuum with a Wien-like peak at very short wavelengths, the implied color temperature jumps into regimes passive dust cannot reach. That breaks the natural passive model. If instead the signal is a forest of narrow lines, Cn and related radicals in the violet structured C2 bands, or even metal lines, then non-LTE processes, electron impact, or plasma coupling can explain the power without invoking blackbody temperatures. Metal line ratios can probe the Fe/Ni balance directly. Alloy-like fingerprints would show blended features and relative strengths that don't match primitive dust. Temperature diagnostics from line widths and excitation states will tell you whether the energy distribution comes from hot grains, pumped molecules, or something engineered to shed heat efficiently. December's Hubble and JWST window is the clean test. JWST can trace the continuum slope into the near IR, while dissecting the blue visible lines via coordinated ground support, and Hubble can resolve morphology that ties color to structure, jets, knots, or coherent surfaces. If the blue persists as a thermal-looking continuum suggestive of stellar-level temperatures, passive models fail hard. If it resolves into narrow, identifiable emissions, we can map the physics through known transitions and plasma conditions. Either way, the spectrum sets the cost of each framework in black and white. So what must the December campaign actually measure to move from speculation to inference? The 10th Anomaly isn't a color quirk, it's an energy audit. A blue-dominated perihelion demands either temperatures passive dust can't reach or non-thermal emission strong enough to drown a red continuum. That's a falsifiable claim against quiet sunlight.